Hi everyone, welcome to another episode of Data Dialogues. I'm Julien Redmond, General Manager of Certus Insights and the host for the series. Today's a bit of a different one. We're actually going to be taking a look at rocket engine development and actually how the development of rocket engines relates to the sorts of things we do in the Data Vault world. But first, wanted to mention the Data Vault Innovators community. That's the technical and professional community that's here to support all of you as professional information management or analytics users. It's really a place for conversations and debates and sharing of information. So we'd really like you all to get involved. Please comment and provide feedback. Get in touch and let us know the sorts of content that you'd actually like to see. It's really based on community principles, so we need your interaction. And since we're now coming through YouTube, please make sure you hit the like and subscribe and click on the notification so that you get the updates as more content is delivered. So talking to the first slide, SpaceX is a really interesting company and I've been following them for a while. And I actually looked into a video that was actually published by the Everyday Astronaut a while ago and decided to share it with my team. And after sharing it with my team, we've decided to share it with all of you. Really has a great conversation with Elon Musk, the CEO of SpaceX. And what struck me was when they were talking, the similarities between the development process for an extremely large rocket and rocket engines aligns very closely to the agile processes we use in Data Vault development. And it just struck me that it was quite a unique thing to realize that similarity. So I really hope that you enjoy this video. Maybe there's some technical terms that you may not have heard before, but really just have a listen for the development process that they use. Find those similarities. I really hope that you find it interesting. I really did.
And remind me, are the grid fins, do they still fold in?
No.
No. Is that going to be permanently that way?
Yeah, so what I'm trying to have us all just implement rigorously is the sort of 5-step process. First, make your requirements less dumb. Your requirements are definitely dumb. It does not matter who gave them to you. It's particularly dangerous if a smart person gave you the requirements because you might not question them enough.
Yeah, you might take it as like gospel, like yes. I have to do this thing.
Everyone's wrong, no matter who you are, everyone's wrong some of the time. So make your requirements less dumb. Then try very hard to delete the part or process. This is actually very important. If you're not occasionally adding things back in, you are not deleting enough.
Right.
The bias tends to be very strongly towards let's add this part or process step in case we need it. But you can basically make in-case arguments for so many things. And for a rocket that is trying to achieve try to be the first fully reusable rocket. There's never been a fully reusable rocket. People don't understand. Like, This is like the holy grail of rocketry,
100%.
okay? And so you really need, you have to run at tight margins because if you don't run tight margins, you're gonna get nothing to orbit.
Right.
So you got to delete the part or process step, super important, and you can't like hedge your bets. That's why the grid fins, for example, do not fold down, because that's a whole extra mechanism that we don't need.
And you can just compensate for it by having strong enough engine authority to steer it in the lower atmosphere.
Actually, our simulations, so we don't really need any extra engine authority. As long as the grid fins, basically follow the flow, they're not really disturbing the flow. It's really neither here nor there.
So
as long as they don't have a high angle of attack, it doesn't matter.
A few degrees or something, or within a degree or two.
So, but in any case, it's a thing we could add later.
Right.
So now these grid fins are humongous. We'll go see them, but they're like a dinosaur bear trap. Okay, it's like a bit of bear trap or a dinosaur. That's what these things look like. And if you have a whole mechanism for folding them, that's like clearly a part that we don't need.
Yep.
So this was a good design decision. That actually I didn't come up with, and it was like great, but it followed the principle of like delete the part, delete the process. And I was like, great, good idea. Let's not fold them. Why were we folding them anyway? Somewhere random, and also if whatever requirement or constraint you have, it must come with a name, not a department, because you can't ask the department. You have to ask a person, and that person who's putting forward the requirement or constraint must agree that they must take responsibility for that requirement. Otherwise, you can have a requirement that basically an intern 2 years ago randomly came up with off the cuff, and they're not even at the company anymore.
Right.
But it came from the, let's say, aero loads department. They're like, actually, no one in the aero loads department actually currently agrees with that. This is, by the way, happened several times.
So again, it can be literally.
I don't want to put it on the aero loads department, but there's like,
Yeah.
there's every department.
Right.
So
it can be thought of as gospel again, but it might be something that's just totally in passing. Like,
yeah.
Or someone played too much Kerbal and had fins at the top of the rocket, and then it just, it did this.
These things are often just way more silly than you'd think.
Yeah.
Anyway, so step 1, make your requirements list dumb. Step 2, delete the part or process step. If you're not deleting a part or process step at least 10% of the time, basically, if you're not adding things back in 10% of the time, you're clearly not deleting enough.
Right.
And then only the third step is simplify or optimize. The third step, not the first step. The reason it's the third step is because it's very common. It's possibly the most common error of a smart engineer is to optimize a thing that should not exist.
Right.
Okay.
Right.
And you say, well, why would people do that? Well, everyone's been trained in high school and college that you got to answer the questions, convergent logic.
Yep.
So you can't tell the professor your question is dumb, that you'll get a bad grade. You have to answer the question.
Yep.
So everyone's basically, without knowing it, they got like mental straitjacket on. That is, they'll work on optimizing the thing that should simply not exist.
Right. Right.
I'll give you an example from way back in the day of Falcon 1. So in the original sort of like, when Tom Mueller and I were like batting around, like, okay, what should this rocket look like? I think I was literally in like Tom's kitchen or something, and we had like the spreadsheet, and like, okay, we need to like make a minimally viable rocket, like half a ton or whatever, it's something like that, and then initially the spreadsheet had we had an NTO MMH upper stage, so sort of hypergoal upper stage, kind of like a variant of the TRW LIMD.
Yep.
So.
Which I think Tom worked on, right?
Yeah, Tom, the people who trained Tom worked on it. He's not that old.
Yeah, that's right.
It was like a baby,
Yeah.
They were a very advanced
he
baby.
designed it.
But his mentors did work on LIMD. So, Lunar Module Send Engine. So, basically a pintle injector.
That's right, because that's where the pintle injector comes in, right?
Because you can also deep throttle it and everything. So, now the problem with that is how much does NTO MMH cost? It's super expensive. Okay, it's like a rare chemical. So even if you're like, if Edison and Tesla had a baby and that baby was smarter than both of them combined and said your job is to optimize an NTO MMH upper stage, you're screwed. Okay. So, like nitrogen tetroxide and monomethyl hydrazine are super expensive, and they're also toxic.
They're super nasty, yeah.
Yeah,
Just the handling costs alone are probably pretty appreciable.
I do think like safety is overcorrected on the NTO MMH. It went from like nobody had any protection and breathed the fumes all day to it's cyanide. Okay,
Yeah.
and neither of those are true. It's not cyanide. You won't die. And Bill Gusmeyer told me like a story of like when he started at NASA, they actually I think passed around like a cup of like hydrazine so that everyone knew what hydrazine smelled like. So like because it's like a rotten egg smell or something like that. So literally an open cup of hydrazine, and like obviously he's still alive. So that's an example of like don't optimize the thing that shouldn't exist. We should not have NTO MMH upper stage.
Right.
Now Dragon does have that, but that's because Dragon's got to do a lot of like nuanced firings of the Draco engines, with very short pulse durations, and if you have trying to have something that's not hypergolic is very difficult. And it can be done, but if you say not hypergolic and not cryogenic, now your options tend to suck.
Yeah.
So, then you start going down the peroxide, barking up the peroxide tree or something like that, and that's or super esoteric monoprops.
Right.
And that's like, again, back to big money. So
yeah. So that's
you know,
step 3.
Yeah. So exactly. So getting through these quite laborious. Sorry for the laborious explanation here, but and then finally you get to step 4, which is accelerate cycle time. You're moving too slowly, go faster. But don't go faster until you have worked on the other 3 things first.
Gotcha.
Like if you're digging, you know, your grave, don't dig it faster. Stop digging your grave.
Right.
But you can always make things go faster. And then the final step is automate. Now I have personally made the mistake of going backwards on all 5 steps, multiple times. So I have to repeat this, yes, multiple times on Model 3, where literally I automated, accelerated, simplified, and then deleted.
Well, I hope you enjoyed that. Did you catch the 5 development process steps that they use? I think the first one, make sure your requirements are less dumb, is a really interesting thing, but I guess it's talking about really making sure you understand what you need to build, and and don't just build things because you think you need to. Leads into that second one of trying to delete part of the process. Delete as much stuff as you possibly can, and if you're not adding stuff back in, you're not deleting enough stuff. And simplify and optimize. I think Elon made the point that lots of engineers will actually try and optimize a process before they realize that actually they don't even need the process. So you definitely got to try and delete the process first, then simplify and optimize, and then work on accelerating cycle time. And I think we'll probably try and accelerate cycle time before we even think about those other 2. So you've got to get it in the right order. And then the final point of automate. And obviously automation in a rocket engine development and production is very different to automation in a data vault space. But we are seeing massive amounts of automation through the data warehousing landscape. And I think we want to make sure that we get those processes right. And then what we have to do is then once all of those other processes are done, is automate what's left. So I think it was really interesting. I hope you saw the analogies. I know that my team thought it was interesting. And we'd love to get some feedback and some comments on what you thought. So please hit the like, subscribe, hit those notifications, and please make sure that you get over to the Data Vault Innovators community site, and make sure that you're registered to receive that communication. There's lots of great content there, and we really want to have good discussions with the community. So please get involved. Thanks for joining today.